lecture within the course on data analytics, we will be talking about clustering techniques. First, let's shortly discuss what we mean under clustering or clustering analysis. So, clustering analysis is an approach where we divide the data into groups that are somehow meaningful or useful. Like, for example, we can see here, we have some data. We don't really know into which classes do they belong or what they are, what is their sort of semantics. But we see that there are some points which are next to each other very closely. Other points are next to each other. Other points are next to each other. And generally, we feel that these points have something more in common than point from here with respect to another point here. So therefore, somehow a logical units, and there could be described, for example, by the fact that the intra-cluster distance is smaller than an inter-cluster distance, meaning between clusters. The distance between clusters is smaller than the distance of objects within the cluster. We can see another example here where we see an example of clustering precipitation in Australia. So there are some regions which have exhibit similar weather, and they are therefore clustered to distinct regions where this similar behavior of rainfall is can be measured or observed. So in general, objects in a group, in a cluster, are similar to one another and different from the objects in other groups. We can use clustering, for example, for gaining some understanding. For example, we can group related documents together. So we have a bunch of documents, a database of documents, and we would like to group them somehow together for browsing through them. That could make sense. We can group genes because of their similarity, many genes, so we group together into a cluster, or protein structures in biochemistry and biology that have some similar functionality. So we can express that functionality somehow through their properties of the genes, and then we can perform clustering in this kind of functionality attribute space. We can group stocks with similar price fluctuations, etc. We can also use so that is where the clustering facilitates directly understanding. But we can use clustering also as some kind of a middle helping system, which helps us, for example, in summarization. If we would like to have some representative subset, very small subset of data or information about the data, then we can use the clustering to summarize us the data and just use the representatives from clusters to perform a certain analysis on this minimal version of the otherwise large data set. And when talking about large data set, if we are in a need of compressing our data into a smaller representation for storage and transmission, then we can use the clustering for compression. Often, we can also use the clustering for example, expressing various levels of detail. And it could be nevertheless also very useful for finding nearest neighbors. Imagine that we are looking for relationships between various objects. Maybe we want to do KNN classification. Well, if we have a clustering available, then checking what are the nearest neighbors to my point in space becomes much less computationally expensive because I have a subset of points I need to look for and not which are within a cluster and not an entire data set. From certain perspective, clustering can be considered as a classification problem. However, classification where the training data does not have a class. So it's kind of, there is no training data really. There is a data set, but we don't know for any of the points which class do they belong to. So it also can be called as an unsupervised classification. So as compared to supervised classification methods, which we discussed previously, like decision trees or rule-based classification, etc. So if we perform such an unsupervised classification, we basically group some data points together, but we don't really know the name of the class which they are somehow together in. But we know that there is some kind of a relationship. There exists some kind of a class. We just didn't give it a name yet. And maybe during the understanding process, we actually find out that that class has a certain specific characteristics and we can give it a name. When looking at clustering, we can have various approaches and we will shortly discuss this here. For example, we can have clustering which is partitional or which is hierarchical. So if we have this set of points here, these black points, we can see that we can represent this as, for example, these two clusters. So these red squares or the blue triangles, this could be a reasonable clustering of this data. So this would be considered, if we will not consider anything below, as a partitional clustering because we have two partitions, one partition and the second partition here. However, we can further actually subdivide this cluster into a subcluster in a higher level detail in more detail. So this is another cluster, this is another cluster, and this cluster we can subdivide into this cluster and this yellow cluster. That means that we actually have several clusters and we have some kind of an hierarchical ordering because this is the supercluster of these two clusters together. And we can go even one level further and we can subdivide this into one cluster, another cluster, the third cluster, and here also three clusters. So we can see that we can have hierarchical clustering, like we can see here, or we can, if we just disregard these hierarchical steps, we can just see that clustering is often partitional. It is relevant to consider how are the data instances associated with the cluster. So, for example, and most common is that one data instance is exclusively fully assigned to one cluster and one cluster only. So we do not have like an instance which is part of two clusters. However, this might be the case sometimes, and occasionally we can have a data object assignment to more clusters simultaneously. And then we call that such a clustering as overlapping. So the clusters are overlapping over some data entities, data instances, and they are belonging to both clusters. For example, if you want to cluster people, whether they belong to category a student and a teacher or a instructor, well, sometimes it might happen that an young instructor decides to take some master classes of a different in a different department and might become himself or herself also a student. In such a case, we will have an overlap that a student is at the same time a teacher while he or she is a student, and that means that we will have therefore an overlapping clustering in such a case. Another approach, similar but different, is so-called fuzzy clustering. Fuzzy clustering means that we have clusters and each object is assigned to the cluster in a partial way or maybe probabilistic way. So it belongs to a cluster with a membership weight between 0 and 1. And so to several of the clusters which are far away, the object might belong with a value 0, and maybe to two or three, it might belong with a value which is smaller than 1. And it distributes its membership among these. It would make sense, and typically is the case, that in this fuzzy clustering scheme, the objects are sum up their membership to 1, so that it's not that some object only partially belongs to an cluster, but it doesn't belong to any other cluster. A complete clustering means that clusters are assigned to every object, or that every object is assigned to at least one cluster, and partial clustering assumes that some data form some uninteresting background which we do not intend to cluster. So that could be also the case that we have some objects which are plotted, but we are not clustering them because they are not within the scope of our clustering, because maybe one of their attribute values doesn't qualify them for becoming members of the clustering analysis. Let's have a look at what type of clusters are we typically dealing with. So one group of clusters are the so-called well-separated clusters, and these are where every object in a cluster is closer to any other object in its cluster than it is to any other object outside its cluster. So we can see that even the point which is closest to this other cluster, this point is still far away from the closest point in that cluster, and it is closer to any other point within its own cluster. These are the well-separated clusters where there is a big gap between two clusters. Then there are other types of clusters which are called prototype-based clusters, which means that in every object in a cluster is closer to a prototype point, which is typically the center of its cluster or centroid of its cluster, than to prototype of another cluster. So that we can see here, like imagine that the prototype point will be here right in the middle for this cluster, and then another prototype point will be here right in the middle of its cluster. And then every point within its cluster is closer to this prototype point than it is to the prototype point of this cluster. So that is the so-called prototype-based clusters, which have, because of their characteristic, have a natural spherical shape or circular shape because they tend to have kind of a symmetric clustering from all directions, approximately the same distance, which is different from well-separated clusters. If they are far away, they can have also other shapes than, generally speaking, a spherical one. Now, let's have a look at other types of clusters. We have, for example, graph-based clusters. So in case we have a relationship, explicit physical or implicit established relationship between objects, objects can belong to a cluster if it forms a connected component with other members of a cluster through its edges in a graph. So a cluster will be simply defined as a connected component in a graph and it can have actually arbitrary shape as long as the points are the nodes are connected by edges. A special case here is the so-called contiguity-based cluster, which is originally maybe not having these explicit edges, but two objects will become connected by an edge if they are within a specific distance from each other, and then each object in a cluster will be closer to at least one another object in a cluster than to any object outside the cluster or to any object in another cluster. Let's have a look at that example here. We can see that this cluster here is, we can see that these points are very close to each other, and therefore they are clustered together, not because they are all closest to some one center point, but because they are mutually closest to each other within this cluster than any points which are here, any points which are here. Then the same holds for the points within this arc structure, where the points are closer to each other than at least to one point than to any other point outside the cluster or inside some another cluster. And that holds also for these two clusters here, which are connected by a dotted uh, set of points, which actually will therefore make this cluster to become a one cluster because it will be connected through these points together into one cluster. Because all these points are very close to each other, and they will be therefore forming this cluster which has two circles and it's connected by this dotted set of points. Finally, we have some so-called density-based clusters, where these clusters are dense regions surrounded by regions of a lower density. It could be defined as that each object in a cluster has several neighbors around itself in a very close neighborhood, and that will define this density. So here you can see that there are points which are dense but not too dense. Here there are points which are denser than these points around it, and here are points which are also denser than the background, or also here. So with the density-based clustering, we will be able to cluster these dense points as one cluster, another dense set of points as another cluster, and another set of points as the third cluster in the more sparsely defined background. This is a dedicated clustering technique, which is called the DB-scan. Now we will be talking about the mostly widely known clustering technique, which is called the k-means clustering. K-means clustering is a clustering method which is parametric. It has a parameter k, which says how many clusters do we want that are created within the data. And then also this clustering is prototype based. So it has a centroid for each cluster, which is the center point within a cluster. And that is its prototype. It could be applied to objects in n-dimensional space. We can cluster points in 1 dimension, 2 dimensions, 3 dimensions, or any dimensions, and the algorithm is straightforward to use in all these dimensions. We can initially choose k initial centroids. We can place them initially maybe randomly in the space where other data points are, and then calculate for all object points in the data set to which centroid do these points belong to. So, and then we can associate these points because they are closest to that centroid. So once again, maybe we have three uh, centroids which we randomly put within the same space where our data points are. And then we go through all data points and calculate their distance to each centroid. And one of these distances will be the shortest one, and that will be determining to which centroid is that point belonging, is being a member of a cluster of that centroid. So we calculate that, and then afterwards, these points, the centroid points, they are not really in the center of the cluster. And the center of the cluster we can calculate in such a way that once all the points are assigned to one of these centroids, these or prototypes, we can then calculate what is the true center of gravity or true centroid for all these objects, which are members of one particular cluster. So this would be points belonging to one particular cluster. And then we will place the centroid in that position. So their prototype will change its position abruptly from where it was to become the center of gravity of those points which were assigned to it. This might mean that for some points, this um, this um, this prototype might leave its vicinity of the points, might become too far away, and that will lead to the fact that the point is no longer the centroid of that particular data point, and that data point might be reassigned to another centroid. And that will mean that we will perform this centroid repositioning for all the centroids, for all k centroids, and move them to their new position. And then we recalculate the association of the points to the centroids and to these centroids. And then based on this association, as there was some change in the groups of our points or of our clusters or members of the clusters, then every time this centroid will be calculated somehow slightly differently, and we will move our old centroid points or prototype points to this centroid position, newly calculated centroid positions. And we will repeat this process until there is no change in the cluster association, meaning that there is no point which will be changing membership to a cluster, and there is no necessity for the centroid to be moved to a new a center of gravity because it already is in the center of gravity of its points from the previous iteration. We can see 4 iterations of K-means clustering. So we have here some points which are not originally classified by any membership. They are just spread of points. And into this space of these points in 2 dimensions, we have placed 3 prototypes, 3 centroids at some particular position. And we can see immediately that for some points, the closest point is this cross here, and those points which are closest to that point might be associated with this distance. So it is always these points are always closer to this point to any other point. And then maybe this crosshair here is another centroid or prototype, and it has its objects which are closest, may be represented by these circles. So the circles belong to this point. And then for the top centroid point, which is the highest in this illustration, all the triangle points will be expressing their membership to this point. And we can see that at this position, um, none of these points are really in the center of gravity to its points. So what will happen for example, this point, it will calculate the center of gravity for all the points, and it will move somewhere here because this will become then the center of gravity, as we can see here. And then we will do that for this point as well, and we can see how it is moving towards these points to which it was the closest centroid, even if they were quite far away. And then we see that as it was moving away towards this denser set of points, it is also somehow moving the membership of, or losing the membership from points which are in this upper cluster here. And this one point, the centroid here, is moving upwards to become the centroid position for its points here. Nevertheless, as the other points are leaving this one big cluster, it becomes more or less a cluster which is represented by only these triangles, so they are closest to this one centroid and not to the other two which have moved downwards. And now we can see that after the second iteration, as we have lost a couple of members for each of these centroids here, there is much more weight or center of gravity for those points which are represented as rectangles, even more here in the center of this cluster. So this centroid moves further there, and even more loses points from that from the kind of the main biggest cluster. And the same is happening to the other right part, where the centroid moves into the area of this one small cluster. And in the final stage, in the fourth iteration, we can see that these centroid points are becoming stable, and no change in membership will be happening anymore, and they will be somehow staying in a center of gravity of their clusters, and that will also lead to the termination of that clustering process, and we will have a clustering of these three areas or regions by respective centroid prototype points and the association to those. So this is the illustrated principle of the k-means clustering process. Now we have still several choices how this clustering should proceed. So for example, in detail, we can think of what type of proximity measures should we be using. Typically, we will be using the Euclidean distance L2 or Manhattan distance L1 for reasonably kind of a spatially defined attributes. But if we are using some other domain, like for example, document analysis, we might choose the different proximity measure as we have discussed before. So the proximity measure itself proximity measure determines the objective function of the process of this k-means clustering. The objective function means it's the function of local search. You can see that our points in the k-means are somehow moving. They are moving iteratively, and it resembles the similarity of this some kind of a hill climbing approach where we are looking for certain optimal value of some objective function. And the same formulation can be applied here too in the case of clusters or clustering, because we can determine by this L2 distance, this Euclidean distance, what type of objective function can we think of? In fact, the L2 norm is associated with the objective function, which can be expressed as of sum of squared error. So sum of squared error means that we take the distance of the any point in the cluster to which it is associated with, and we calculate the Euclidean L2 norm distance with the cluster center. We square it and we sum it up. And then we do it for one cluster, and then we sum it up, sum this error expression over all clusters, and this gives us some quality measure of our clustering scheme. And the cluster center is calculated here as this average position of the points to which it belongs to. So if we have two different clustering on the same data, we can assess which is better by comparing with their objective function. And in this case, it will be the similarity measure. Centroids are calculated, as I said, as the mean value of the cluster members, as we can see on the second equation below. So these two equations on the bottom are expressing the sum of squared error, which I described, and then also the more detail on how to calculate the center of a cluster, which is an intuitive um, uh, way how a centroid can be calculated. Now, for documents, this is no longer the case that the proximity of the L2 norm or L1 norm will be a good idea. Instead, we should use some other proximity function, which could be, for example, based on cosine similarity or based on the Jacquard coefficient, as they are more meaningful. So the asymmetric attributes would have much more meaningful similarity measures in the form of cosine similarity or in the form of Jacquard coefficient. And I am showing them here again, these similarity measures, but you should remember them from our past lectures. And the objective which we want to maximize, previously, we wanted to minimize the sum of squared error. But in this case of cosine similarity, we want to maximize the similarity and of documents in the cluster to cluster centroid point. And that can be expressed as the so-called total cohesion measure, where we can see here we have the cosine similarity calculated between the centroid and the point in the cluster. And this cosine similarity is then further summed up over all clusters, and it forms a measure which is not called sum of squared errors, but total cohesion. And we want to maximize the total cohesion in order to find the best clustering for our given data. The central problem of k-means clustering is twofold. There are two problems. First of all, it is a parametric method which requires us to express how many clusters do we want. But we might not know in advance how many clusters do we have in our data. So our selection of K might be just an educated guess, and therefore we might have more or less clusters in the data. And then based on this choice of K, we might have some more or less optimal clustering. This is one problem. And the second problem is that we might choose initial centroids in the clustering such that they are not very ideally placed, and they realize suboptimal clustering. So for example, with a random initialization, we can have some example where if two clusters receive the same, which are somewhat well separated, receive just one centroid, then like we will observe in this case here, then these clusters might end up having the centroid between them. So even if we don't have the problem that this cluster and this cluster forms three clusters and we have three centroids to place them, um, we know that there are three clusters here only because we see it, but normally the algorithms doesn't. And we will see that what does the clustering do. So as this cluster here is also a cluster, or the centroid here is a centroid for also these points, it will be dragged out of the center of this cluster here into this middle space between these two. And that will lead also, and also for this point, as it has most points over here on the top, it will kind of move a little bit upwards, which will lead to losing even these points here from its cluster association. This point is moving sort of laterally, slightly downwards to go into the center of its points. And what we will observe here is that now 2 points are stored or centroids within this one big cluster. And then there is this 1 point which is in the middle of the 2 clusters serving as their centroid. And in the last step, we can see that this point is moving a little bit downwards again, but still we can see that we didn't really recover a situation where this cluster center will become really in this center, and it will kind of become a stable point here and will be forming the centroid for these two true clusters. So this is a problem which we need to have some kind of heuristics associated, which will try to resolve this problem. There could be a solution which might lead to satisfactory outcome in the following way. We can initially put one centroid in the random position. Then we sample the data set and put another centroid into a position of the furthest sample point. And why do we sample is maybe twofold. One reason is we do not want to go through all the points. And the second is that if we sample, most likely we will not sample outliers because they are so few and it's unlikely to pick them as samples. And therefore, we will, if we choose the furthest sample point, we will likely not this will not lead to placing the second centroid above an outlier. Because if that would be the case, then and the outlier is very far away, then we will basically have that one centroid to become the centroid of a single point, the outlier point, and that will form a single cluster. In some sense, it makes sense to put the outlier becoming a cluster on its own, but often in cluster analysis, we are not so interested in outliers. So this sampling method is an effective way how we can avoid the outliers to creep into this selection of the initial points. Then, in the next step, we will repeat this and we will select another sample out of the samples, which is the farthest sample from these other two already placed centroids. And we will repeat this and we will always choose the furthest point far away for the remaining centroids until we place all the centroids in this strategy. If a centroid is placed in such a way that no points are assigned to it, although it is placed above a point, so it would need to be replaced to the furthest point to any current centroid. It might happen at some point that a centroid will not have any points because it's somehow uh, pushed away from the centers of clusters, and suddenly other um, centroid points will take up its role. Imagine like we had this one point previously between two clusters. Now, if suddenly there will be two other centroids placed in those clusters, then this point will have no points assigned. And if that's the case, if that happens during the clustering, k-means clustering process, we need to take that uh, uh, centroid and move it to the furthest point to any current centroid, as we had this logical approach in this initialization scheme. And then we will have a good initial position, and then we can start performing the k-means clustering and assigning the points to the centroids, and then repositioning them into the center of gravity of the points they are associated with. Outliers can be often also just removed before the clustering even is performed, and after observing that some points, or during the process actually, after observing that they are contributing to this sum of squared error in unusually high value. So if we have some points which are having extremely high value contribution to the sum of squared error, that will indicate that this point is an outlier, and we might simply just ignore them and remove them from the clustering process. We can also perform some, as this clustering, generally we have different results depending on whether we are, what is the initial position of our clustering points. So in order to get the clustering result out of some local optimum, we can perform a certain rearrangement of the clusters, which might help to get out of the local optimum by, for example, splitting some clusters with the highest own sum of squared error. So the cluster itself has the sum of squared square errors, and we split the one with the highest value. And as the next step, we can, after we basically move the centroids, we can then merge those clusters together, which are influencing the total sum of squared error the least. So if we will be merging, we for sure will have the sum of square errors increasing a little bit, but we can choose to merge those two clusters where this increase in the total sum of square error will be the least. K-means clustering here was now applied in this basic algorithm in a way that we had it applied to the whole data set at once. And then we found some partitioning scheme or assignment of this different centroids to different data points in the partitioning way. What we didn't mention is that this algorithm is not hierarchical. It is a partitioning clustering originally. But however, what we can also do is that we can take a centroid and put it to a or several centroids, and associate them with certain points, and then just add one point to the object points or data points out of our data one by one. And then we always assign that point to a cluster, and then we reposition the centroid based on which cluster has been uh, this point has been added to. And that could mean that we also are moving some points from one cluster to another. So, but we have a guarantee in this way that all clusters start with a single point and no empty clusters are produced because all points are above at least one point to which they will be always the closest, or they will return to that point in a way. Um, then once a point is added, cluster centroid is updated, and if a point shifts between clusters, then it updates two centroids. So the shift between of a point between clusters will update these two centroids, the one which has been moved from and the other one to which cluster it moved to. And we repeat this process and add points until we have all the data points added to the clustering algorithm. This is an interesting approach and has the following interesting property, that it is hierarchical. So it actually um, uh, has the different points can be seen as they are added to the clusters, or we can see it as kind of building some kind of a hierarchy of points. The point on the first bottom was the lowest point, and it was added with another leaf of the second point, and so on and so on. And it could generate basically this kind of hierarchy of adding points together. Um, but the kind of a disadvantage is that this incremental way is a sequential way. We can also say it produces an order of on which points are added, and the clustering will be heavily dependent on this order. So therefore, it would be good, in order to have this somehow a random process, that we randomize which point is added to the data set next from the data set points which have not been yet assigned to any cluster. There is one variant of k-means clustering which is having slightly different approach than the standard k-means algorithm, and it is called the bisecting k-means. So it starts with assigning the points to two clusters, and then it selects one of these clusters to be split. So we can see that here we have assigned uh, 2 points to the to two clusters, and we have these two clusters. This is one cluster, this is another cluster, and then we decide which of these two clusters should split. Maybe because of their sum of squared error is higher. So then we choose the larger cluster. So for example, we can see how many elements has one cluster and how many elements has another cluster, and we can split the one which have more elements. Or we simply decide to split the one which one has the largest sum of squared errors. This could be one or the other strategy, are both valid choices. So in the second step, we might decide for some reason that we split this cluster into two, and we set the two points of with the strategy maybe of the furthest point within its own cluster, and then we will have a clustering which will result in this situation. So we have now three clusters, and then we might have again the strategy of either a cluster size or the largest sum of squared errors, and then we also split the other cluster and we repeat it until k clusters are produced. So after bisecting is completed, we will have our clustering finished, and this way we can also avoid some local optima where the clustering will be sort of the cluster centroid will be stuck between two clusters. After clustering with this bisecting approach, we actually have only locally calculated the sum of squared error, but we do not really know the overall sum of squared error. And that means that after the bisecting is completed, we should proceed with the standard k-means to get a minimal values with respect to total sum of squared errors. And if we will record the sequence of how we created the clusters here, for example, we just had two in the beginning, then we had the three, and then we had the four, we can actually represent this sequence as produced clusters as a form of hierarchical clustering. So this bisecting method actually allows us to create k-means clustering which will have a hierarchical structure, which was not the case in the previous k-means clustering, which was of the partitioning nature. Overall, k-means clustering has a modest both space and time complexity requirements. It is, as we can see, has here m is the number of points, so it scales linearly with the number of points, and it is the complexity, space complexity, of course, affects the k clusters, and then it is also scaled by the n attributes. So this is a modest space complexity. The time complexity is defined by the k times m times n, and I is the number of iterations which we need until we receive some stable positioning. Now, here are certain artifacts which can be associated with the k-means clustering. For example, if we have different cluster sizes, like we have here in this case, that we have the one cluster here, a small one, another cluster here, a small one, and a big cluster here, and we have three cluster centers, still the algorithm might choose to actually stay within the region of the large cluster because it's the cluster, the big cluster is somehow generating a balanced sum of squared errors. So even if this sum of squared errors will be small, and if this centroid will be here as a sum of squared error will be small within that cluster, there will be a large sum of squared error for this big cluster if the centroid will be here in the middle. And that will lead this these centroids here to somehow creep into this huge cluster to balance out this total sum of squared errors. So this is one possible problem. The other possible problem which we might have is the difference in density. So we can have a less dense area and we can have some more dense area, and we can see that this area with the high density will be also through this sum of squared error objective can cause us that we will have here two centroids within this one large cluster or the sparse cluster, while we will have only one centroid point for these two dense clusters, and therefore the centroid ends up in between them. Finally, clustering objects which are non-convex, like for example this half circle type of shape and this another half circle type of shape, will be clustered in unsuccessfully or not adequately with our clustering approach. We would expect that this one shape forms one cluster and this another shapes for another cluster. But for our clustering algorithm, as you can see, it will generate this kind of prototype-based clustering, so which will be roughly in its shape of the domain of the association of the points with the centroid will be roughly spherical. So although these two clusters obviously have some kind of non-convex shape, our k-means will not resolve this. The solution to these problems generally is to use more centroids, to use more k's, and then we will have as a solution, for example, that this one big cluster will have several of its centroids, and therefore there will be also opportunity for one centroid to be in this isolated cluster. And the same holds for this case, and actually the same holds for this case, because if we have enough of centroids which will perform clustering of roughly convex region, we can see that this part will be clustered on its own, this part might be clustered on its own, this part might be clustered on its own, and therefore we will have three clusters forming this type of shape, and three clusters maybe here, and that will lead into desired clustering. However, it will be a little bit more fragmented. We will also very shortly introduce the key principle behind hierarchical clustering. So hierarchical clustering is an approach which generates a clustering in a hierarchical fashion so that it creates a hierarchy of how this clustering has been generated, which can be useful for being able to find a desired degree of clustering, like fragmentation of the data clusters to a size which we want to for particular task. So it generates these clusters in one of two ways, either bottom up, which is known as agglomerative clustering, and it's the most common, or in the top down approach, which is the divisive scheme. In the divisive scheme, we will start with the full data set, and then we will split it into two halves, and then we will further be splitting up the parts to achieve more and more clusters until we reach the individual points at the very lowest level of this hierarchical clustering scheme. The agglomerative clustering starts with all points serving as individual clusters, and at each step it merges two pairs of clusters, which are the closest ones. So for the first step, this is kind of obvious. We will find the 2 points which are closest to each other, and we will merge this into a cluster. So we could employ, in this case, a Euclidean distance. But the question is, what does it mean, closest pair of clusters? How do we express the closeness of clusters? We will discuss it in the next. Before that, it is interesting to observe how this clustering is being built in these two forms of some kind of schematic or conceptual visualizations. So let's have a look at the right. We can see the so-called nested diagram, where we can see that the points P2 and P3 have been put into a cluster first. Then this cluster has merged with another cluster, which was the P4 point, into another cluster. And then finally, we merged with the last point as the third as the next third level of cluster. And we can observe this type of hierarchical clustering approach in this way, also schematically, how this merging has been happening. And this type of visualization is called a dendrogram because it resembles similarities to how neurons are sort of connected to each other. And then this is giving us a clear view how this merging happened. Now let's have a look at how do we express the closeness of two clusters so that we can perform this agglomerative step until we merge all the clusters together just into one big cluster. And then that will be the stop criterion for this hierarchical clustering scheme. So we can use for the as a proximity measure in the hierarchical clustering various schemes, like for example, min or max or group average. Let's have a look at what does that mean. So the min would mean that we are looking for 2 points which are from the clusters closest to each other, and that would express the distance of 2 clusters. So we measure the distance of among all cluster pairs in such a way that we identify the closest points from each cluster to each other, and then we measure the distance. This could be one expression of expressing the distance of 2 clusters. The max scheme is that we actually don't find the closest points from those clusters, but we find the um, furthest 2 points from the clusters, and that will be expressing the distance between 2 clusters. The group average approach is an approach which takes the distances from all points within one cluster to all points in another cluster. So we have always pairwise distances between all the points between clusters, and we will perform an averaging of all these edges length, and that will be expressing the distance between 2 clusters. All these schemes sound reasonable, and we can employ any of those in order to express the proximity and then to merge those clusters which are closest to each other in the next step. However, if we have the so-called prototype-based view on our clustering, we can also express the proximity by means of the prototypes of those prototype-based clusters. So the prototypes are points, the centroid points of our clusters, and we can measure the distance between the prototypes of these of pairwise of each of among all clusters, and we can use the closest distance of prototypes as expressing them as being the closest clusters to each other. Within this prototype-based approach, we can also employ the approach that can be based on minimal sum of squared errors increase when merging 2 clusters. So we can also not measure the distance, but measure the increase of the sum of squared error, and we want to overall have the minimal sum of squared error in the prototype-based approach, and therefore we will choose those 2 clusters to merge, which will increase the sum of squared errors in a minimal way. So this hierarchical-based clustering is therefore a simple method which generates us the clustering. It's in that sense, a parameter-free measure or clustering approach, because it doesn't really require any specific parameter to be set. And we can use within a particular hierarchical clustering implementation a desired choice of the proximity measure, which will be used in this agglomerative sense, so that we can gradually, from individual points, create bigger and bigger clusters, put them together, forming these hierarchies, and then we can use this clustering to explore how does do the clusters look like, and what is the relationship between clusters, like which two clusters are somehow forming some kind of a relationship of parent-child or of a sibling relationship among clusters. This all can be valuable information as a part of the data analysis. Finally, we will shortly discuss the main representative for the so-called density-based clustering. In the density-based clustering, we would like to cluster a certain dense region which are surrounded by a region of sparse points. And we want only those points which are contributing to the dense region to be forming the cluster, while the sparse region in the background, so to say, will be not part of that cluster. So how can we go about that? Well, we need to define the property of a density somehow, and then this density will be the guiding approach for deciding on the clustering. So we can express the density for a particular point in our uh, data landscape uh, by counting the number of points within a specified radius epsilon. So for each data point, we are looking at a certain radius epsilon, which is a small neighborhood around that point in an n-dimensional space. It could be 2 dimensions, 3 dimensions, or more, or 1 dimension. And then we are within that radius, we will be counting how many other points are within that small little circle or ball in 3D. And then that will be forming us some kind of a density threshold. Density, therefore, depends on how do we specify the size of the radius, and because for too large um, radius, many points will be always covered, and even this in the sparse regions. And for too small radius, each point will become alone in the neighborhood of epsilon. So therefore, we need to somehow specify this radius in a good way. So the classification of points given a certain radius will be giving us an information on whether we should put that point as a part of the cluster or not. So we will have this classification based on some parameter epsilon and based on some parameter k. So these could be chosen user parameters, but also one can be somehow derived from the other one. So we will have one classification of points will be that there are core points. The core points are those which reach the minimal number of points k within the radius of epsilon. That means that that these points will be part of a cluster. Then we have specific points, which are so-called border points, which are not reaching the necessary number of points in their neighborhood, but they have been counted as points contributing to the core points neighborhood when analyzing their nearby core points. So we take each of these points within our data as either being a core point or being a border point or being the noise point, which is does not reach the necessary density threshold of k neighbors around its neighborhood epsilon, and these noise points will be ignored in our clustering approach. So once we have established this classification for all our points, we can perform the density-based clustering. The density-based clustering most famous algorithm is known as the DB-scan. So you might hear this abbreviation sometimes. So, and the principle of the DB-scan is that once we have all the points classified, for any two core points which are within an epsilon distance with each other, so one is within the region, like we can see here, one is within the region of the epsilon of another one, like for example, these would be some core points, and A will be some core point also itself. So within, any two core points which are within epsilon distance establish an edge between these core points. So if the core points here are all core points, the A will be connected to this, to this, to this, to this, and to this point. Then all of the connected points will belong to one same cluster. So we don't have all the core points to belong to one cluster, only if they are connected through their neighboring points together and form this kind of connected component. So basically, the DB-scan will be forming a connected component analysis, and then this connected component will be forming the cluster. And then to this initial cluster, we will add all border points that are within epsilon to a core point and are added to one corresponding cluster, because these border points actually could be somehow close to two uh, regions or clusters of core points, but they can be only added to one. So maybe to the one to which they are closer. And finally, in order this algorithm to be specified somehow, if we choose like how many neighbors do we want to typically have to check in the neighborhood, that will sort of imply us in the dense region. That will sort of imply us what neighborhood should be setting this epsilon to. So we can set it in some conservative way so that every point in the dense region will satisfy the property of having at least k neighbors within the epsilon neighborhood, but we should not make it too much bigger, because then we will also include some noise points. So the choice of epsilon given k is based on basically the knn, k nearest neighbor distance in the dense region. We can see here that we have also in this illustration also this border point, for example, characterized, and for example, we might have also some noise point here, which will be maybe this point, which will not have other points within its radius distance. So, and with this, we very shortly characterize the density-based clustering approach. And now we have covered all the most characteristic clustering schemes, such as k-means clustering, the hierarchical clustering, and finally, the density-based clustering. And this concludes our discussion on the clustering algorithms, and we will see each other on the next lecture within the data analytics lecture series.